coming. I was lucky enough to already chat a bit with a few of you during lunch, but not with everyone, so maybe I should start indeed by introducing myself a little bit. So my name is Renata, and I finished my PhD here at the University of Antwerp a little over a year ago in topological data analysis, or TDA, that you will learn a bit about today. And I am indeed, when I first started my PhD, it was still the Department of Mathematics and Computer Science, but it soon got separated, and I'm technically at the Department of Computer Science. But in this group that is at the city campus in this Beacon building, so I am completely separated from this campus and the Department of Math and even the Department of Computer Science, which I find quite sad. So I'm always very happy when I get invited here to give a seminar and just to interact a bit with all of you. So thank you, Arne, once again for the invitation, and to you once again for coming. So the title of the talk, what I will tell you a bit about today, is distance in flats, persistence, homology, transforms. Let's say transform. So after my PhD, I went 1 year to Paris-Saclay for a postdoc. And this is the paper that I primarily worked on during my time here. So this is what I will tell you about. We put the paper on archive already a year ago, still haven't submitted it, under a very different title: Shoving Tubes Through Shapes Gives a Sufficient and Efficient Shape Statistic. I hope also this other alternative title will become clear at the end of the talk. So I like to give this talk a bit by starting first with a big overview, which is a bit unusual because only then I will take a bit step back and tell you a bit how all of this actually came together, or motivation, if you say. So this overview kind of consists of 3 parts, where I first tell you what persistent homology is. I've never specifically instructed me multiple times that I should start with this. So I will tell you what persistent homology is and why it is cool, what we can do about it. And for the second part, I will tell you what persistent homology transform is and why it is even cooler. And then finally, as a third thing, I will tell you what all of this is: distance from flat persistent homology transforms, which is basically our contribution, which is what this paper involves. Okay, so I said I start first with persistent homology, or PH for short. So how I will see this, I will write it in a specific way for a specific reason that will become obvious pretty soon. But we can see this as a map that takes some function, it's a real function, you will see it more in detail, and maps it to a so-called persistence diagram of some space X with respect to this function. And we are looking at a specific, homology degree. Okay? And this was introduced by Vanessa Robbins in her PhD thesis, so around 25 years ago. So this domain, and in the domain of topological data analysis, or TDA in short, and persistent homology, it's almost like synonyms. So persistent homology is the main tool in TDA, but it's basically what TDA kind of revolves around. And as you see, it's a pretty young domain, especially in math. We would say that it's very, very young. So what is it? I'll spend some time now with on the x-axis, we have the so-called birth values, and on the y-axis, we have the so-called death values. And everything lies above this diagonal because something needs to be born first before it dies. So what are these values? Well, these birth and death values are the values of this R here, where the cycle is first seen in the data, and the death value is when it dies. So here it would be basically the birth value would be the length of the longest edge, leave it around to connect it, and then if you increase this R, other things start connecting like these, and then at some moment we don't see the loop anymore. So what would be the persistence? How do these persistence diagrams look like here for this X? Is, well, we would have, in the beginning, when you look at R0, you have 20 different components. So there is 20 of them, but soon they start merging. And what you will end up in the end is that one of them will live forever until infinity. So we have some kind of infinity here. We have a special line for this. We will have one. We will have one point here in the scatter plot, and then we will have a bunch of other ones here close to the diagonal that die right away because they start merging with another one. So things that are close to the diagonal typically don't matter because they are the distance between persistence diagram kind of ignores them, makes them less important. And then what we will have here, we will also see this one loop. When it is born, as I said, it's born where we have the length of the longest edge, so maybe somewhere here. And it also, it dies basically where the radius is of this loop. So we have some. Yes, please.
So, is it correct, am I correct in assuming that then there's a point in the diagram as soon as you have some trivial homology?
Yes.
The rank of the...
Yes, the rank, indeed, the Betti numbers. So basically, so that's exactly what I was going to say next. So in the persistence diagram of degree K, the number of these points in this scatter plot in the persistence diagram is the Betti number. So here we see there is one connected component in our data, and there is one loop. So this is homotopy equivalent to a circle, so that we know. However, this is what I was saying. I think that the idea of the original inventors of persistent homology was to do that, to capture homology of discrete spaces. But you get additional information here. So it's not only homology because it's not just the number of points that you have, but each point has a birth value and a death value. And this is additional information, which is typically geometric, actually. So it goes beyond topology. What is it here? The birth and death values, which, well, I already told you. So it's the kind of reflecting the sparsity of these points. So it's giving us the longest edge. And it's also giving us the death value here, for example, of the loop is the radius. So it's telling us about the size of the loop. So it's more than just homology. I think this is important, and this is quite confusing for a lot of people because also the name is topological data analysis, and the tool is persistent homology. So we are stuck in this topology world, but actually there is geometry captured here. We are not in this, so for this paper, we are not in this setting of point clouds. We are actually in the world of shape analysis. So you said that you like shape analysis, so this is going to be interesting for you. So our X is actually going to be a constructible set, which means that it's definable and compact. It's just that it's not too wild. I mean, this is basically the only restriction that we have. Because we are in the context of shape analysis, so we want to kind of capture shapes and be able to retrieve shapes, and, well, capturing point cloud, retrieving a point cloud is not so interesting. It's just a finite number of points. And this F that I mentioned is a function that goes from this shape, or this constructible set X, into the set of real numbers. Here, and this function, if you look at the sub-level sets, so I can write it like this. These sub-level sets, they will result in this so-called filtration. So we also have some kind of an underlying function there that I didn't show you. I mean, here it's just Basically, it's distance to point cloud, but it's a bit of a different setting. So maybe just to rewind here for a moment, if we are calculating persistent homology for some object X, the input of persistent homology is not X itself. We actually need the so-called filtration, so a nested family of topological spaces that are describing our X at different scales. But basically, most of the time, you actually are looking at the shape X and this function. Or I mean, you can just look at the function. And it will define immediately, the sublevel sets will define filtration. So this is the only thing that we need. So I'm also going to give you an example of I call this filtration function. It's not necessarily an official term. That is more interesting for our setting, so that we a bit practice this persistent homology. So imagine that you have some 2D shape. This is the shape. So there is, I mean, just to say, there is infinitely many possibilities how to build this filtration. So if you take any shape X, you can look at it through many different filtration functions, or many different lenses, or many different perspectives. How you choose this filtration is crucial, because the information that you get with persistent homology are going to be influenced by which choice of filtration you make. Now, a particularly interesting filtration for this paper and this world that we're living in is the height filtration. Which basically takes and it just maps it to a scalar product with some unit vector v. I mean, so here, if you look at the unit vector v being this one here, it kind of means that you are just scanning this shape from top to bottom. And you can look at any unit vector. So if we are scanning from bottom to top in this case, what will the filtration look like? Well, you are coming from here, there's nothing, and then you see just this point, and then you see this, and then it starts increasing, and you see this, you start seeing this, and so on, right? So these are going to be these sub-level sets of the height function. So what will be then here the persistence diagrams? Again, we have persistence diagram in degree 0 and persistence diagram in homology degree 1. So what will they do? So as I said, like here, there is nothing, and only when we come here, a connected component is born. And then it's there, and it basically lives forever. So it is born, let's say that this is that one. So here we will have one component that is born at 1, and it lives, this is some kind of, and then can we calculate this one together? So, can someone tell me where will the first loop be born, approximately at which value? So we are coming like this, like this, like this. Do we see the loop if we are here? No. Do we see it here? No. Do we see it here? No, because you see that the shape will just, what you see is just this. So it's contractible. So you need to come all the way to here, right? So I don't know what if let's say it's 5 or something. And then it also lives forever. It lives until infinity. So we will have like some kind of a point here. This is also infinity. And then the other one will be born a bit higher, so maybe around 6. So when you look at these persistence diagrams now, to summarize, what is this persistent homology telling you? It tells us immediately, okay, this shape that you're looking at has one connected component and it has 2 loops. And as I said, with this additional information about the birth and deaths, it gives you additional information, which is typically geometric. And in this case, what is, for example, here, what are the birth values telling us about these loops that we see? Yeah, like the relative position in the space, because here it was the size, for example. Here it is the position. So that's what I'm telling you. The choice of filtration influences what these birth and values mean. And it's typically some additional geometric information. Okay, so now we can go back to.
Because if you choose different filtrations, sorry, if you choose different functions, you can construct the shape of your shape.
Wow, you are going really fast forward, amazing. Yes, exactly. That is the whole point. We will see this in a couple of steps. But yeah, great. Yeah, maybe this is a good moment indeed to stop because I will not spend more time on explaining persistent homology itself. So if you have some questions, now is the time to go.
Isn't there also going to be a second component at some point? The whole, it's just final that you get two blocks.
Where are you?
A little bit higher.
Yeah.
There.
Yes. This is also a bit, I wanted to not have this scenario, but it's actually going to be very important. Yes, here you will have a one that is born, you're very right. So the first one, we said it's born at the second one, if we have this, right? So we're at this level. It will be born, let's say, at 2 and it will die at 3. So we will have another one. Yes. 2, 3. Okay. I told you that I'm also going to tell you for each of these things why they are cool. First here, why it is cool. I'm just going to write it maybe for now like this. So persistent homology gives some information about topology and geometry. Why is this cool or useful? Well, maybe to come to the example, where can we use this, to the example that you mentioned, Agne, during lunch about cancer research. I mean, the persistent homology, it can have applications in any real world problems where topology and geometry are useful information. So for example, if you look at the cancer applications and you look at images of certain cells in the human body, you can, from each of these images, extract its persistent homology and use some machine learning, for example, any classification algorithm to solve it. So it's kind of a way to represent images in this case. So any possible application that you go to, if topology and geometry matters, persistent homology might be useful. But you don't need to only restrict yourself to like these real world applications where you're calculating persistent homology on, for example, images or point clouds. Now I started a postdoc where I'm trying to use PDA, or basically persistent homology, to understand something about deep learning. And there I'm looking in particular in the first part at decision boundaries. So I'm not looking at the data itself, I'm looking at the decision boundaries, and I'm calculating persistent homology of the decision boundary, because if the decision boundary, it doesn't, yeah, maybe if you're not familiar, but in any case, if the decision boundary is something more complex, the models tend to struggle to generalize. So this is kind of the idea, okay, I can see with the persistent homology how complex is the decision boundary. So for example, if you see from here, persistent homology might not be able to differentiate between, let's say, these three things, because they all have a one connected component and one loop. So for me, in this problem where I'm looking at decision boundaries, that's great, because I only care if data can be separated with a hyperplane or a line, for example, or the data is, I need a bit more, I need a loop of some kind to separate the data. So this is for me, I don't care if it's a triangle or if it's like this. Well, if it gets really curvy, then I do care, but I will also be able to capture this. But just to say that in some applications, like this problem that I'm working on right now, or in cancer research, whatever, it might be actually beneficial that you don't differentiate between these things. So you get some information about topology and geometry, but you don't get all the information about the shape. And that is sometimes useful, because this additional information might be noise for that problem. Okay, but we can't actually squeeze out more information. So now we're coming a bit to what you were saying. if I'm using this approach here, how can I squeeze out more information about my shape? Here I know of something, but I mean, if I draw the shape completely differently, like this, it could be the same. Well, without this thing now here that came a bit unexpectedly. So how can I here get more information with this approach? I think we're maybe thinking in a similar way, but yeah, I don't want to rotate. I want to recover the shape completely. And when I say shape, I mean this constructible set. So I want to know exactly how it is positioned in the space, and so I don't want to have any kind of invariance with respect to this.
Use different functions like the distance to
Sure. So that's indeed like now you're going to the third step. So I want to come first to the second step, but it's great. I love that we are already thinking further. So the idea here, look, I just was scanning my shape from bottom to top, but I could also scan it from top to bottom, from left to right, from right to left, or basically any direction. So instead of just looking at this direction, I could look at all directions, all possible directions. So this is then, yeah, exactly. So this is the next step where we are looking at persistent homology sets. So what is maybe here, yeah, I actually wanted to write it more like this. Oh, whatever, it doesn't matter, I'm just going to leave it. But here the idea is that pH of X gives some information about topology. But it doesn't give complete information, so we see if we can do a bit better, which is fine sometimes, but sometimes we want more information. So what is PhD doing? Well, it takes as a input the sphere, and it goes to the space of persistence diagram. So we take a unit vector on the sphere, and we map it to maybe I just write one because we always start with this one. I can go. So now we are looking at all possible directions here. So here, all possible directions on the sphere. And for each of the directions, we calculate persistence diagram in all homology degrees. We put all of this information together. And then why is this? So this was introduced by Catherine Turner, Sajan Mukherjee, and others around 2020. And what they proved, so why this is cooler is that they have a theorem which shows that this PhD is injective. So if you take two different shapes, X and Y, their persistence homology transforms will also be different. Meaning basically that what you already said 5-10 minutes ago basically is that PhD of X gives complete, maybe is a sufficient descriptor of shape. So it gives us complete information about the shape. And I think this is really a cool result because people, when they hear about persistent homology, I get this very often, is they think about holes, so you have inside the loops, the voids, and so on, and they think persistent homology can only capture that. And then they think, but then it's only useful in applications where you have some loopy structures in the data. But actually what you see here, that by using persistent homology, you can describe your shape completely. So basically, if you're interested in shape analysis, imagine that you have a bunch of shapes that you need to classify. You can represent each of the shapes with its persistent homology. PhD. Yes.
So this is injective from quality of shapes, not even homeomorphism of shapes.
Yeah, equality of sets.
Quality of sets.
Sets, yeah. So it is, yeah, the most that you can do.
Yeah.
Yeah, it's not isometric up to isometric.
Wait, take a step back. Like what is so this map is injective,
Yes.
right?
Yeah.
So this means that two vectors cannot land in the same. These are points, right? These P, D, K are just these orange points.
No, this is a whole like scatter plot.
It's injective. If you take the spaces as input, two different spaces.
Yeah. So see, this is injective, PHC. So if you take two x and y to be different, the PHC of x will be different to PHC of y.
So not the map from S and -1 to N?
No, not this map. No,
They send
so
X to a map.
yeah, no, not that one.
Yeah.
So actually, yeah. No, I'm just thinking always how to match the three different parts, how I represent them. So I have to think like always what is useful.
Can I ask you a very, very big question? I mean, if you want to describe a function, a shape, you might have this equation, you have this data. Then you know that you can describe it completely in terms of persistent homology. Do you have some sort of advantage in doing that? What is the advantage of describing it in terms of persistent homology?
Because how will you otherwise describe it? Yeah, especially, I mean, maybe especially in applications. So I want some kind of an object that I will feed to a classifier in a machine learning algorithm. What you normally want to feed to machine learning algorithms is vectors. You want to have elements in Hilbert space. Typically, that's the most desired property. So you want, how will you represent your shape as a vector? And this, I mean, persistence diagrams is also not a vector. So this is not a vector, as I told you, it's a scatter plot. This is a really nasty object. It doesn't lie in Hilbert space. It doesn't have a unique mean. It's a bit of a mess. But there is many ways that you can transform this into a vector very easily. You can just put a Gaussian on top of it and have some kind of an image, and it's fine.
So you have a classifier, you feed an image, for instance, so pixels, and where does this persistent homology? I mean, do you train it to get back, or?
I mean, you could do it, but I mean, like for images in this case, you don't necessarily need. I mean, for images, if you're classifying a set of images, I would not necessarily use this because an image is already in a vector. I mean, it's a two-dimensional vector, but you can just like flatten it and you already have the pixels, so it's fine. You might use this for images because in images, that's what I was saying. There are sometimes applications where you don't want to have all information about the shape. So if you're looking at images, there's typically a lot of noise. I mean, not noise in maybe a typical way of thinking, but noise in the sense of what you're trying to solve. So irrelevant information. So you typically don't want to represent, in many applications, your image exactly. So you know that, like maybe, for example, indeed, whether there are loops, that might be some kind of cancerous tissue that is developing. So that's interesting to capture. So then you might do this. And how you would do it is that you don't feed to the classifier the image, all the pixel values, but you feed the persistent homology of that image. Okay. In this case, if you're now looking at shape classification, so you have like really complicated shapes, and imagine, I mean, this is an R2, but we can be in any arbitrary dimension. So how are you going to feed a shape, a constructible set, to a machine learning algorithm? There is many shape statistics, so people use many different shape statistics, but these are pretty rudimentary. So, and in this way, you can describe it completely. So you're getting just a vector representation, basically. That's what I would say, of complicated stuff.
So it's before the classifier.
Before the classifier, yes, yes. It's what you feed to the classifier.
Yeah.
Okay, so this is all stuff that has been out there in the literature, as you see, for 25 and 10 years. And then we come to our contribution, so what we actually did here. So what we introduce, when you look at this is in the literature called persistent homology transform. But first of all, why would this name be reserved only for this? Because here you see I'm looking at this. Yes, please.
Can I ask?
Yeah, before I move on, yeah.
You could also take x cross Sn minus 1 and see it as one shape, right?
Yes. Okay.
And then form a function on that bigger space, right? Like the little f. I mean, you're taking just against this b and you're moving the b, right?
Yeah.
I think there is a global function from x cross Sn minus 1 to r that does exactly this on each fixed b.
Yes. Okay.
So then, can one relate this function of these, PDs all the way where you move the b to one single one for a bigger dimensional space? Does this make sense? I don't know.
I will have to think a bit about it, but you are constructing there, if you look at this product, I mean, the idea is that I want to represent this shape. I mean, if we're talking about what was just the conversation, I want to get some kind of, let's say, vector representation of this. I'm interested about x, so if I'm taking a product of x with the sphere, I'm getting another shape that I'm studying.
It's any slice, right?
Yeah.
But my question is whether, I mean, I'm trying to figure out if you're tricking me here with number 2 or not. If this is like a real, somehow varying this v really gives you something new, or it's just, something that lives in a. Yeah, anyway, okay, no. I don't know. Yeah, it's just.
I think it will maybe also become a bit clear also when I come back to the motivation. Remind me, and I will go back to that question. But yeah, I'm not quoting you.
Okay.
But, at least not on purpose. So yeah, as I said here, this is in the literature called persistent homology transform. But immediately you can say, like, why would this name be reserved only for this map? Because notice here that I'm making a very particular, very specific choice on how I'm going to filter my data or my shapes. So I make a very specific choice on the filtration function. And I spent quite some time telling you that actually we can look at many ways. We can look at whatever function f. So why would the name be reserved to it? So we can actually generalize this, this notion. So what we say here, we now, from now on, refer to this as the classical or height persistent homology transform. But we can actually look at any space as input, a topological space. And then do the same. I take some function that is parameterized by elements in this space. And then I map it to, so there is no reason why this notion of looking at multiple directions or the notion of persistent homology transform is reserved only to this particular choice of function. So we generalize this and we say that basically here this is it has the, what is different is this. You see that this is different and then this is different. So this one here will basically be and then H. So we call this then the classical or the height persistent homology transform, and we call this the generalized persistent homology transform. And a lot of the results that we prove them for the generalized case. But the main idea here that we introduced also this term is that we hope that now in the following years, people will also look at different filtration functions. So just to broaden a bit the perspective that it's not only the height. But in particular, we focused on one case where so the domain is the Grassmannian of all affine spaces of dimension m. If you are not familiar with it, I will say what it is. And we take a certain flat here. And we do the same thing. But now we're going to have this flat. Coming to the title slowly. So we are looking at a particular persistent homology transform where we make a particular choice about the domain and about the filtration function. So what are these two things? Well, the Grassmannian of the affine subspaces of dimension m. So for example, if m is 0, this is the set of all lines. Sorry, here it would be points. Points are a dimension 0. Points in Rn. If n is 1, these are lines. I mean, this is a geometric interpretation of that. If you look at these spaces. And then M2 will be planes. So just to see if like anyone is still awake. Planes, and then we go to n minus 1. So these things are called flats. So this is the domain. I mean, I think it's a bit slight abuse of notation compared to what you often find in literature on Grassmannian affine spaces. So we're not too used to this one. And then this filtration function that we look at is just distance from a flat. So it will be
So you take a shape in Rn, you take like a subspace of Rn, and you move this.
no. So I will show you. I mean, we will now come a bit more to what this means, but maybe I'm thinking like this, but I wait 2 minutes to answer this question. First, I want to say, to conclude this overview, to say that the final thing is that I promised, which is why this is the coolest now, or why we think it's the coolest. Do you have maybe any ideas? I actually doubt it, indeed. Not that I won't undermine you, but just because of the things that you work on, I think you're less focused on practical implications. But why do you think it could be cooler? So here I told you that this classical PHC that was introduced 10 years ago is already giving us complete information about the shape. So how can you do anything cooler than that? Do you have any ideas? Because maybe it will give me ideas what else we could also try to achieve.
Not sure if it's an answer because this is generalized what they this seems like
No. No. It's somewhat related if you look at hyperplanes, but it's not the same. No. We proved it. We proved the relationship explicitly. No. We can go into it a bit more once we start understanding intuitively what it means, that I will now refine. I just want to conclude here why it is the case. This is this indeed, like, of course, this generalizes this. I mean, because here you just take the sphere and you take the height function. But this is not a generalized version of this.
But I mean, if n is 2 and n is 1.
Can you say it again?
If n is 2
Yes.
and m is 1,
Yes.
right? So you're choosing
Yes.
a line, and then you're looking at the distance.
Yes.
So if you take as little b, you know, like a unit
No,
vector in that line.
you will see now on the.
minus signs.
You will see on the next. I promise that this will be clear why it's not, but it's a good
But
question.
is any in a, you took any in a.
It's almost the same except that
Yeah.
probably at minus.
Yes, exactly. I will make all the drawings. Yeah.
Ah.
You squeeze it. It's kind of like squeezing in between the two. If you look at distance from a line, you have bounded from both sides, and the height will not be bounded from both sides, only from one. But I will make the drawings. But I mean, I love this that you're all going a bit forward. Maybe just to conclude here, and then we will come to these questions.
Yes. A suggestion from Felix online, is it perhaps more computable?
Yay! Thank you, Felix. Yes. I was just wondering, well, how am I on time? Okay, then I will basically be able to make some sense. So here, what we show, so here it was a classical PHC. So this one with the height function. And what we show is, we also show the similar result. So we show that it is injective. This distance from flat is injective, but we don't really show it like that. We show that this one, but truncated to homological degrees up to m minus 1 is injected. So we just have an additional thing where we are able to look at less homological degrees. Now, why is this cooler than the previous case? Well, calculation of persistent homology in degree k is exponential, grows exponentially with the degree k. So the less homological degrees we need, the better. And actually, it's not only that. If you look at the particular case of when m is 1, so if we're looking at lines, then it means that you only need to calculate homology degree 0. And homology degree 0 is even nicer than all the other ones because there are specialized algorithms to calculate, which are so much faster. So if you're looking at lines, you only need homology degree 0, and you're getting all information about the shape. That's really cool because, so basically what we are now having is that PhD, this distance from flat PhD, is sufficient and efficient shape descriptor.
Okay, so,
Yes.
so this function PhD
Yes.
takes any topological space that I can conceive together with a function.
In this case, we're looking at constructible sets in Euclidean space.
Plane.
No.
No.
Any dimension.
Any
Oh,
dimension.
Euclidean
Can be more
space.
than n, more than the homology degree that you're looking at.
In these cases, all the other ones will be trivial, so this is why we don't have any. But yeah,
What then? I mean,
so my x that I start with, what I wrote here is,
okay. It's
Yeah.
the same.
Yeah.
All right.
maybe that was missing, yeah. Okay, now I will make all these promised drawings. I want to, because I have only 10 minutes. Is this what you use? Or does this work on itself? No, so I will have to use that. More used to these dry ones. I feel like that they work a bit better. Oh, this is nice.
It's a blessing and a curse.
Yeah. Okay, so as promised, I want to tell you a bit how this came about. I mean, it didn't just fall from the sky. I wish I was that smart that I could put this just like this. The idea came actually from our previous work, which was primarily experimental, where the idea was to see what kind of problems persistent homology is really good at solving. And we looked at 3 problems. Can it detect holes? Well, of course, that should at least work. That was fine. Can it detect curvature? This was because there was already a paper a few years before that proved that this could be done. And then also convexity. Can persistent homology, so that was the kind of motivation. So can persistent homology detect convexity? And I think that the expected answer at that moment was no, because I mean these things were never really like put together in research. What my idea was to look at this height function. Why? So if you look at some kind of a, I'm not sure what I want to do, but okay, like this. So this is my shape, which is concave. So if I'm looking at this height function, in this case, from top to bottom, what happens, what you noticed already before, I didn't want to have that scenario, but I drew my shape by mistake a bit, not ideally for that setting. But here, if you start scanning from top to bottom, for a certain while, you will see these two connected components. Also, we will still see them here, we will still see them here, and once we come here, they will merge into one. But the persistence diagram in degree 0 will have at least two connected components. So my idea was that if EB0 has one connected component, X is convex. And if it has more than one, the shape is concave.
Rule B.
No, so yeah, that's the thing. So I will also explicitly say the theorem once we actually get to it, but the idea is that X is convex if and only if for every direction persistence diagram has only one connected component. Because for concave shapes, you just need to find this one direction. I mean, for concave shape, there must be at least one direction where we will see this. So that's the theorem. Okay, but this works here, but it doesn't really work in every case. Can you think of an example, and let's keep it for now simple, we can find an example in the plane, I can already tell you. So in our tool, that is concave, but where that will not fold. Yes, indeed. So something where the concavity comes from some loop inside. So if you have a shape like this, I mean, it can be whatever, but something like this. It doesn't have to be like circles. I mean, obviously. Try to scan it from any direction of the sphere. You will always see one connected component. There will never be multiple. Then what my initial idea was, so if I look at the sub-level sets, I mean, there will be, what was that? So then my idea was like, okay, it doesn't work with the height. Let me adjust this height a little bit. Let me look at the absolute value of the height function. So the absolute value of the scalar product. And then what you end up with if you choose your direction wisely, you're like here you have some kind, you start scanning, you will have something like this. Because what is actually a height function, what you were also saying, you're looking at everything below a certain hyperplane, everything up to minus infinity, let's say, and then everything above a hyperplane up to a certain level r, like this r from the sub-level sets. But here we can say, let's not look at everything below a hyperplane. Let's look at everything below a hyperplane, but only up to my level of r, and everything above the hyperplane also. So you're squeezing it basically between two hyperplanes. So this was still like, okay, I'm just adjusting the height a little bit, it works. However, this also doesn't work. So can you think of an example where also this doesn't work? And maybe a little bit of a...
Take a point instead of down.
Yeah, no, I don't want, yeah, okay.
No, that doesn't, it's not that much.
Yeah, it's, I mean, you will, do you want to allow this kind of like wild spaces? I mean, just listening, but you will still have it. I mean, if you squeeze in this line, you will technically have these two intervals on the side, so it would still work. I can tell you that actually you can prove this theorem. So this is what we initially did. We did this, but then in R2. So in R2, this does hold. So don't think of R2. You will not be able to think of an example. Go one dimension higher. Yeah, you can actually even do simpler than that. If you look at just the sphere. Sphere is concave, we have a certain void inside. If you look at the standard height, what you will get is something like this right on top. So it's one connected component always, just keeps increasing. what do you get here? Even if you try to be a bit smart like this, and you put some kind of a hyperplane in the middle, but you will get this. And then it goes also a bit. So you will get some kind of a ring. So it's always, again, one connected, even though we squeeze it between two hyperplanes. So then what we do?
Lines instead of hyperplanes.
Yay, lines instead of hyperplanes, indeed. Because now if you shove some kind of a line here, so this is the, and you start growing the R, what you will end up with is these, I don't know how to draw this. These two disks that are lying on the polar opposites of the sphere. So you have two connected components, and then they grow, and eventually they merge into one. So the theorem, maybe for the sake of preciseness, that we proved in this previous paper was that if you have, I think we made an assumption then that it's triangulizable. And then basically the X is convex if and only if for every line, I'm going to now write it. We didn't think of Grassmannian at that moment. For every line, the persistence of homology in degree 0 for X with respect to this line has just one connected component. So if you find a line with there's two connected components, we know for sure that the shape is not good. So then we introduce, like, this is basically the height. This is like absolute height. So we just take absolute value of this. And here we call this the tubular filtration. And so we introduce a new filtration because as you start growing around the line, you get these tubes. It's like you have to shove tubes through shapes. And then basically, yeah, I have 2 more minutes to wrap up. So this was already from the previous work. But then we realized there is no reason why we need to only look at lines. So we can rather actually look at flats of any dimension. So it doesn't have to be a line, it can also be a plane or a hyperplane or so on. And basically we were wondering if this is true. So if you look at here, I mean the case 0 is a bit particular. I don't necessarily go into it because I don't understand. But we were wondering that if you go higher and higher, will you need more homology degrees? And it is indeed the case. So here you only need homology degree. Here you only need homology degree 0, here you need homology degree 1 and 2, and here you will go up to n minus 2, because it's up to n minus 1. And the classical, it needs also the final one. So basically all of ours, any distance from flat is computationally better than the classical. But the lower the m, the more computationally efficient it is because we need less logical degrees. Okay, maybe I stop for now because I want to at least leave some room for questions. So you see now that it's